You've all been introduced already to dynamical mean field theory. And what I would like to do in this lecture is to give you a little bit of a forward-looking picture about the sort of thing we can learn from it in the best cases, what predictions can be made with the theory, and where do we go from there? Because, you know, you're the new generation. You have to take these sort of theories to the next step. This is sort of my ambitious plan for the lecture. It's not clear I'm going to be able to go even halfway through it, but let's see. I want to go back a little bit on the main concepts, which are the heart of DMFT. That was beautifully introduced, I'm sure, by Olivier already in his lecture, but perhaps you will. It's good to repeat things and to see this with a slightly different perspective. Then I'm going to elaborate on one of my favorite materials, transfer ruthenate, as really a very nice test lab for these sort of approaches. Hugo has already mentioned this in his lecture, but I will say more. This will be the occasion for us to discover sort of new route to strong electronic correlations, namely the effect of the Hund's coupling. So I will elaborate a bit on what we call Hund metals. If I have time, which is unlikely, but I will talk a little bit about much more delicate properties at low frequency, which would allow us to calculate transport properties of materials. And then I want to give you a little bit of an overview of what's beyond single-site DMFT, extensions and generalizations. So let's see how this will work out. This is a bit of an over-ambitious plan, but let's see. Okay, so first, kind of a refresher on dynamical mean field theory. And in DMFT, there are, you know, in this acronym, there are sort of important letters. The first one is D. So D is a little bit confusing. You may think that, oh, the whole theory is about non-equilibrium properties. D is really there to mention, to signal the thing that we are interested in frequency-dependent or time-dependent response functions, but first in the original framework of the theory at equilibrium. So it's really important to realize that in contrast to many static mean field theories, like mean field theories in usual StatMech for, say, a magnet, or density functional theory, or Hartree-Fock, in contrast to all these theories, DMFT is actually an energy-dependent mean field. And it treats different energy scales in different ways, and that's really a very important aspect of theory. And of course, the MF aspect of it, the mean field aspect of it, is because there is a locality principle. So we are using locality as a guideline. The theory is good when things are local enough. I will come back to what that really means in practice. And the notion of locality implies that we can do some mean field approximation on the spatial correlations, which of course may not always be sufficient, and that will be the end of the lecture. Okay, so one thing I want to insist on is that in this school here, you're exposed to a lot of computational methods, which is excellent. And DMFT is indeed a powerful computational framework, but it's also a conceptual way to think about a condensed matter system, about a material. So it's both. It's really a theoretical and computational method to actually do concrete calculations on a given model or material, but it's also a conceptual framework to think about materials with a perspective which is slightly different with what you find in many solid-state textbooks. Indeed, if you open, I don't know, Mermin Wagner, Ashkoff Mermin textbook, what you will see is that in chapter 1, you're introduced to materials as being made of atoms. And then between chapter 2 and chapter 45, the atoms are gone. And you are basically only talking about an electron gas subject to some sort of interactions which are mostly annoying. So DMFT takes a very different perspective. It says materials are made of atoms, and we're going to keep this at the core of our thinking until the end. So we're really thinking about a material made of atoms. This is not a big discovery. We know materials are made of atoms, but we're going to keep that idea throughout. So the same way that usual mean field theory, say for the Ising model, replaces a whole lattice model by one entity coupled to a bath, you've understood from Olivier's lecture that dynamical mean field theory replaces this collection of atoms, which are connected by hopping of electrons, by the problem of one atom in an effective bath, and the effective bath is a self-consistent one. But you should really think of each atom as a little many-body problem, right? So the spectrum, the electronic spectrum of an isolated atom is actually not just filling the energy levels of a hydrogen atoms with independent electrons, right? There are many-body interactions. It's a small many-body problem in itself. Actually, if there are many electrons, it's not such a small many-body problem. And the eigenstates are correlated eigenstates, which often in jargon are called multiplets, okay, which are these many-body eigenstates of an isolated atom. So please keep this in mind in the follow. Okay. And so everything relies on this concept of embedding. We're going to have an atom with all its many-body eigenstates exchanging electrons with a bath. And that part of the theory is exact in principle. There is no approximation there. If somebody who knows a lot about nature gives me the local Green's function of a material, so what I mean by local Green's function, it's a bit of a sloppy terminology. What I mean is that if you give me the full Green's function, which is g of r prime omega, and I project it, you've been introduced in the previous lectures to this notion of projectors, which define the embedding. So I project it onto a specific set of correlated orbitals. I take matrix elements of g of r prime of omega. That defines g local. So you give me g local. I can construct an impurity model which exactly reproduces this g local. And I can do that by adjusting the hybridization function delta, which is this quantum generalization of the Weiss field, so that G local is the solution of the impurity model for that given delta. So that's the concept of embedding, and it's a representability assumption. Okay. It's a bit on the same conceptual ground than in density function theory. We say that the local charge density can be represented by a free electron system in a cone-sham potential that we adapt to reproduce rho of R. And the two key differences with say DFT is that one, we are representing a quantity which is a full function of energy, while rho of R is just a static quantity. That's difference one. And the second difference is that the representation system we pick is not a free electron system, but it's an interacting system. Okay? And we do that to be able to reproduce the exact eigenstate of the atom or the atomic shell we consider in the limit where the hybridization would be 0. Let's say when there is no hopping between sites, we want the atomic spectra to be exactly reproduced. Okay, so this is the concept of embedding, and in principle there is no approximation there, except that I've put under the rug a subtle question, which is that when I say that we can do this representation, it assumes that we know which local interaction we have to put in the impurity problem. And DMFT does not give a prescription for that. If we deal with the Hubbard model, we know the answer, we just keep the same U. But if we are in a solid, which interaction matrix elements do we have to put in this local impurity problem? Single-side DMFT in its original version does not answer these questions. Somebody has to give you these effective interactions. We'll see tomorrow in the GW+EDMFT session that extensions of DMFT to this sort of formalism, GW+EDMFT, gives you an answer to that question and gives you a prescription for actually computing these interaction parameters from ab initio. But at that point, we are not dealing with that in this lecture. Okay, so probably Olivier already showed that, but this is sort of a conceptual, a little table which gives you the conceptual similarities between different kinds of mean field theory, namely usual mean field theory in StatMech, the first line here, sorry, the first column here, density functional theory and DMFT. In each of these cases, we have to define a local quantity. Here is the local magnetization, the local charge density, the local Green's function. We have an equivalent system which serves the purpose of representing that quantity, so spin in an effective field, electrons in an effective potential, quantum impurity problem. And we have the notion of a Weiss field, which here is the original Weiss field, the local effective field. Here is the Kohn-Sham potential, and here is the effective equalization. So there is a perfect conceptual similarity between these different forms, these different theories. Okay. Now comes the approximation. The approximation, in order to close the loop and be able to compute self-consistently both delta and G, and hence also the self-energy of the problem, is making a locality assumption, and the locality assumption, colloquially speaking, is that the self-energy is a local quantity in real space, or is momentum independent in momentum space. And once you've done that, you can completely close the loop through a self-consistency condition that specifies that the local Green's function is in the solid actually should coincide with the impurity Green's function computed from that embedded atom in a bath. Okay, so actually, I want to insist on the fact that this sort of quick sentence saying self-energy is local, when it comes to real material or to a system that has more than one band or more than one orbital per side, has to be taken with a grain of salt, and this is something which is really important. When, as you saw yesterday, when dynamical mean field theory in the realistic materials context was introduced, and the notion of projectors was introduced, for a specific material, we have to define the embedding by a choice of correlated orbitals that span the sub-Hilbert space that we call the correlated subspace, right? And when we say the single-side DMFT approximation is to approximate the self-energy by a local quantity, what we mean is that the self-energy is local in that basis of correlated orbitals. Of course, if we upfold the self-energy to the whole solid through these projectors that connect the full Hilbert space to the local correlated Hilbert space, if we promote the self-energy, if we upfold it to the whole material, then the self-energy acquires momentum dependence. And so this equation here relates the self-energy, say, upfolded to the block basis. We could upfold, or the Kohn-Sham basis, we could upfold it to any basis we want, but here I've taken the example of the Kohn-Sham basis psi nu k. And here is the self-energy in the local orbital basis. So we take this quantity. The single-side DMFT approximation is to actually postulate that this thing can be well approximated by a k-independent function, locally in real space. But when we upfold it to the whole solid, because of these matrix elements here, it acquires momentum dependence, right? So these matrix elements are nothing else than the projectors, pk, m, nu, that you've seen yesterday in the lectures and in the tutorials introducing MODEST. Okay, so I'm insisting on this because I'll answer your question in a second, because it can be, and it's often the case, that these matrix elements can have very strong k-dependence, and hence this guy here will acquire very strong k-dependence. We'll see an explicit example of this in a minute. Yes, please.
I'm not sure what is meant by chi being dependent on k.
Oh, yeah, good question. Yes, absolutely. So chi-m is, say, a local atomic orbital, so you may want to think of it in real space, right? Chi-m over r, right? But I can always take a Fourier transform of this, right? And think about it in k-space as well, right? So for example, if my chi-m's are maximally localized Vanier functions of some sort, right? Then chi-mk would just be the U matrix, that, the unitary matrix that rotates the block basis to the Vanier basis, right? And it's a k-dependent U matrix, right? So chi-mk would just be, U mu k psi nu k, okay, summed over nu. That's what I mean. I could have written this equation in real space as well. Okay. Good. So this was just a refresher about the formalism. And now I would like to insist a bit on the D in DMFT. Why is it important in correlated materials to work with a mean field theory which is energy dependent? Okay. And the reason for this is because in a correlated materials, if we are interested in spectroscopy, and in fact, DMFT is to a very large extent motivated by understanding spectroscopy, the key quantity is the local spectral function, which is energy dependent. The nature of the excitations in that spectral function at high energy is very different from the nature of the excitations at low energy. Imagine we have a metal, a correlated metal, right? We know from, standard textbook physics, Landau, Fermi liquid theory, and so on, that at low energy, we expect the excitations to be quasi-particles. Right? And quasi-particles are basically dressed Bloch waves of electrons, right? Which propagate like waves. So they are really waves. But if we think of high energy excitations, high energy means that the excitations involve very short time scales, right? Then the excitations are of a different nature. They are much more atomic-like. For example, if we take a material like strontium BO3, which you've been exposed to in one of the tutorials, and we look at the photoemission spectrum, so this is the photoemission spectrum of K-integrated of strontium BO3, you see two kinds of excitations. It's a metal, the Fermi level is here. It's a metal, so there are some density of states for quasi-particle excitations, which are here. Right? But there are also some higher energy excitations. So here at negative binding energy of about minus 1.5 eV, there is a peak, right? And this peak has a very simple interpretation. This material has one electron in the D shell of vanadium. You do photoemission, you just remove that electrons. So in terms of an atomic excitation, it's just D1 to D0. It's just removing an electron from that atomic shell of vanadium. But you see that these excitations, which are high energy, you can think of very easily in real space as just removing an electron from a specific atom. While those excitations here, you have to think of much more as waves in momentum space. So DMFT is precisely aimed at retaining these two aspects. And if you want to be slightly emphatic, you can say that it really implements the particle-wave duality of quantum mechanics at the core of the theory. Okay. Right. And so you've seen in Olivier's lecture, I think, this one of the first early success of DMFT was to provide a description of the Mott transition, which captures both low energy Landau quasi-particle excitations at wave-like at low energy, while maintaining the description of high energy Hubbard-like bands, which are these atomic transitions, and the transfer of spectral weight between the two. So this is just a caricature of actual computations. I think Olivier showed that little movie probably of how the spectral function changes as you change the coupling. You start from a half-field band. Let's say you increase the coupling. Gradually, the quasi-particle bandwidth, which is the width of this thing, gets smaller and smaller. And the corresponding spectral weight is transferred from these quasi-particle states to these Hubbard bands. And at some point, the gap opens, and it's an insulator. There are no longer only low-energy quasi-particles, and the only thing that remains are these atomic-like excitations, which are called Hubbard bands. And the total spectral weight, because just the spectral function is conserved, right? So there has to be transfer spectral weight between these different features. Okay. So here I want to pause a little bit and give you some view of what this really means in terms of the effective impurity model that describes this process. And the magic word here is the Kondo effect. So I want to elaborate a little bit on this because I think that magic word was probably not so much pronounced in the previous lectures. So I want to elaborate a little bit on this. So imagine there is no bath, right? And we are at half filling. Then my impurity model has a ground state, which is doubly degenerate, because we can have, this Hubbard atom, which is just one level, can have four configurations, either 0, up, down, or doubly occupied. 0 and doubly occupied are high energy states, right? And up and down are the low energy states, and they're exactly degenerate if there is no bath, right? So we have a doubly degenerate ground state on each side, which means that if we have a collection of these atoms in a lattice, we have a 2 to the n degenerate ground state. And of course, this cannot be true when we start to turn on hopping, or if you want the hybridization function, because we're not going to, ground states are not exponentially degenerate in nature. The degeneracy has to be lifted. In fact, and that's a sidebar, but many interesting phenomena in quantum condensed matter physics come when you have a large degeneracy which is lifted by some perturbation. This is the case of the quantum Hall effect, for example. A large degeneracy and interactions lift that degeneracy, and something interesting happens. Okay, here is the same thing. We have this large degeneracy. We turn on the hybridization with the bath, and what happens to this doubly degenerate ground state? So what happens is that this degeneracy is immediately lifted, and the local moment, which is this ability of the spin to flip between up and down, no longer exists, right? What happens is that an electron from the bath comes and screens that local moment by forming a singlet ground state. So the ground state becomes unique, it becomes spin 0, right? And if you want, what happens from the point of view of the impurity model is that this local moment is swallowed by the bath, and the ground state has spin 0, not spin half, like in the no hybridization case. So that phenomenon is called the Kondo effect. When you have a bath which is made of a continuum set of states. It's a gradual effect. If I am at high energy, I see the doubly degenerate ground state. So, for example, if I measure the susceptibility, it would be Curie-like, 1 over temperature, because there is a spin that flips. If I go down to low energy or low temperature, I'm going to cross over to a susceptibility which is Pauli-like it should be in a metallic system, because the ground state is a singlet. So that's the Kondo effect. And the whole thing from going from high energy to low energy is the story of how this local moment gets screened, or if you want, how the degeneracy of that local problem gets lifted as we go down to low T. So that's the D in DMFT, is describing this process of gradual screening. If we are at high energy, the quasi-particle peak, or when I'm saying high energy could mean high temperature. So at high temperature, the spectral function will not have this quasi-particle peak here. It will be just something like this, with kind of a pseudo gap, no quasi-particle excitations. And as we go to low energy, low temperature, this quasi-particle density of state is gradually going to grow, signaling the screening of this doubly degenerate entity. Okay? That's the whole idea behind the theory. Everything I just said is possible if the bath delta of omega has states near low energy. So that will apply to metals. If, on the contrary, the hybridization function is gapped at low energy, like in the multi-insulator, this process of lifting the degeneracy is not possible, because there are no available states in the bath to do that. And this is what happens in this regime of the DMFT equations. Here, the bath has no states at low energy. The bath is actually very similar to the spectral function of the system itself. It has a gap, and then self-consistently, the Kondo effect cannot happen, and the system keeps a local moment, which can eventually lead to long-range magnetic order in the lattice, which DMFT can also describe, but that's a different story. Okay. So you see how the mode transition in DMFT can be thought of as a self-consistent Kondo effect and self-consistent breakdown of the Kondo effect as we reach the multi-insulator. Any question about that? Yes, please.
Just to try to have an intuitive understanding. In the Kondo problem, we have this formation of this quasi-particle peak, and as you described, this is related to the screening that we see of this isolated impurity.
Right.
But when thinking about the Mott transition, when I start from a net lattice and then I'm using DMFT, we also see the emergence of this quasi-particle peak. And you're saying the same thing, we can observe this screening within our
Yes.
DMFT approximation, is that right?
Yeah, what I'm saying is that the DMFT the DMFT equations, which map everything onto a self-consistent Kondo problem, a self-consistent impurity problem, right? Embody a self-consistent Kondo screening of the impurity, right? Which is due to the fact that delta of omega resembles the spectral function itself. So if you are in the metallic phase, the spectral function has states near zero energy at low temperature, which is the quasi-particles, means that delta of omega also has states at low energy, and the Kondo effect is possible. Right? While if you're in the insulator, delta of omega has no low energy states, and hence the Kondo effect is not possible. Right? I'm not saying that the effective Anderson impurity problem at the heart of DMFT is mathematically the same than the standard Kondo model with a large density of states. I'm just saying it's a self-consistent Kondo process in which the bandwidth of the bath is reduced as you reach the mode transition.
Okay. I was just wondering if I could see properties of screening in my sample. I think that's what
Well, okay, so I use the word screening in a bit of a perverse sense here, good point. What I mean by screening is screening the local moment. It's not screening in the sense of screening of the Coulomb interaction, right? People use colloquially the word Kondo screening to mean that the local moment is actually swallowed by the bath. Okay? It's not screening in the sense of screening of the electrostatic potential, which will be the topic of tomorrow's lecture.
If I try to map out the hysteresis with this coexistence region coming from the metallic regime,
Yes.
I have a finite density of states
Yes.
omega equals 0.
Yes.
So shouldn't I always get the Kondo effect and never go to the insulating solution?
No, so in the coexistence region of the theory, there are actually two solutions, right? There is one solution in which delta of omega has a gap, and the spectral function also has a gap, and another solution in which delta of omega has no gap, and the spectral function has no gap. So in both cases, this fits the description on the slide, right? But there are two distinct solutions, and these two distinct solutions do not have the same free energy. You just have to compare them, right? And one wins over the other, depending on parameter space, which defines the transition line. But there is no solution such that delta of omega has a gap, but Kondo screening applies, right? There's just two distinct solutions. Gap delta, gap A, gapless delta, gapless A. Are distinct solutions of the system. Right? They are just local minima of the free energy, then you have to compare the energy. We can discuss that offline more. Okay, so now, how does this extend to the multi-orbital case? Yes? Do we have what? Okay, now you are asking a sophisticated question, I guess, which is, can the Kondo screening process be more involved than just what I just described for the single band Hubbard model? And the answer to that is yes, and this will come in the case of strontium ruthenate. But if you are a bit patient, you will see that later in the lecture. No. If you have a multi-insulating state, yes, okay. So the question was, I think the question was, can you have a multi-insulating state with a bath that is gapless? And the answer is no. If you have a multi-insulating state, the bath has a gap, together with the actual solution of the problem, the spectral function of the problem. We could go into more complex situations where you have a multi-orbital system in which some orbitals behave like metallic and some orbitals behave like insulating. That's called orbital selective mode transition. The whole field of research, we can discuss it offline. But I'm trying to keep with simple things. Right? Okay. So now, how does this work when we have multi-orbitals? So here is an example in which this little circle here is supposed to represent the atomic shell of a system. It turns out that this is sort of relevant to this strontium ruthenate metal that Olivier mentioned and Hugo mentioned, where the electron can exist in three different orbitals, which are the three quadrants of this circle. And this material turns out to have 4 electrons in its shell in the ground state, right? So now you see that for the isolated system, the degeneracy of my local atomic shell is much bigger than 2, right? In in the case of the Hubbard atom, it was up or down. Here, what is the degeneracy? Can somebody answer that question? 9. Who? Yeah, that's excellent answer. Indeed, 9. Why is it 9? Because you can put that doubly occupied state in either of the 3 quadrants, so that's 3. But also here you see that the ground state has spin 1. It has spin 1 because of an interaction which is called the Hund coupling, which I will introduce later, which favors maximal spin, which is 1 in this case. And because it is spin 1, it's a triplet, and hence the degeneracy from the spin point of view is again 3, 2s plus 1. Right? So 3 times 3 being 9. The ground state of the isolated shell is 9-fold. But that system is a metal. So it doesn't have a massively degenerate ground state, right? The ground state is a gas of quasi-particles, Fermi liquid, with a unique ground state. So the whole story of the flow of the system from high energy to low energy is how we go from a massively degenerate state of 9 to the n configurations down to a system, to a low energy ground state, in which all degeneracies have been lifted. And now we don't have to lift just a degeneracy of 2 on each side, but a degeneracy of 9 on each side. Right? And in that case, the process which consists in lifting this degeneracy, or if you want the generalization of this Kondo process to this multi-orbital situation, can be more complex. And we're going to see later in the lecture, if I ever get there, how this happens. Okay, so the way you can think about this, and again, this is the D in DMFT, is what the local impurity problem does for you is to monitor the history of quantum jumps between the different configurations of this atom. So let's say we start in the ground state here. This is the ground state configuration of this 3-orbital atom. Then we now have an electron reservoir, which is my effective bath. We can lose an electron to the reservoir, and for a certain amount of time, the atom will be in a different valence state, which differs from this one by both charge. This guy has 4 electrons, this guy has 3, and spin. This guy has spin 1, and this guy has spin 1/2, right? So we have valence transitions which change the quantum numbers. At some other point, we have an electron, say a spin down electron from the reservoir, which will hop back, right? So we are back to the same charge states, 4 electrons, but now this guy has a double occupancy, it's a higher energy state, and so it has spin 0. Right? And what the impurity model does for you is to actually monitor this sequence of quantum jumps between these different valence configurations. Right? And it is, of course, the history of these quantum jumps which will eventually construct the low energy physics of the system. Okay, so if you want to represent that in some cartoonesque way, you can think of DMFT as describing the flow from a very high energy regime where you have atomic configurations and multiplets with this massive degeneracy. As you flow down to low energy, right? The environment, the coupling to the bath, which really means electrons hopping around in the solid, okay, lifts this degeneracy and lead you to some collective ground state, which could be, for example, a metallic system, or could be an insulating system if you are on the other side of the mode transition. And eventually, this state can have other instabilities like ordering. Okay, so this is a bit of a cartoonesque slide, but I think it's useful to think about it, about the theory in these terms. Okay. So now I'm going to switch gear and I'm going to show you in practice how this sort of high-level description applies to a concrete material, namely strontium ruthenate. Are there questions about what I just said? And of course, I'm advancing super slowly, but this is good. You have lots of questions. Okay, good. So let me illustrate everything I just said on the example of strontium ruthenate. So why strontium ruthenate? Well, Hugo said a few things about this morning. It's a remarkably clean and beautiful oxide. I like to call it the Drosophila of strongly correlated oxide. You know, the Drosophila is this little fly that people in genetics like to use because it's a very nice model system for genetics. So this material is a very nice model system for anybody interested in correlated electron materials. Why is it the case? Well, primarily because it's a beautiful system to do experiments on it. You know, our field is a field in which experiments are absolutely important. And often it is the case that it's difficult to do the same experiments on all the families on the same material. Like, for example, in cuprates, you can do excellent photoemission on BISCOR, but it's more difficult to do photoemission on LSCO. So, you know, some members of one family are actually better suited for that type of experiments than the other. But here, it's a quite unique example in which a single material is so clean, the crystals are so good, that you can do all the battery of condensed matter experiments on the same single material. And one of the reasons for this is that the single crystals that can be grown of this system are huge. They are unbelievable. You see, this is a single crystal grown by Yoshima Eno many, many years ago in Kyoto, and it's 10 centimeter large. This is crazy. So you can do neutron scattering on it, on just a single crystal, and you can do all sorts of beautiful experiments like quantum oscillations at low T, transport, and so on and so forth. So we basically know virtually everything experimentally on this material, which also means that if, as theorists, we cannot explain the properties of the material, then we're in trouble. The other reason why this material is beautiful is that it has a very simple crystal structure. Well, this may not appear so simple to many of you, but people familiar with cuprates will immediately recognize that this is the same structure as lanthanum 2 copper 04, perfectly tetragonal. It's a single layer perovskite with these beautiful ruthenium O2 planes, which are analogous to the copper O2 planes in lanthanum 2 copper 04. So you see these ruthenium O2 planes here, which are made of a ruthenium atom surrounded by 4 planar oxygens and 2 apical oxygens in these elongated octahedra. And of course, importantly, this is also a very interesting material because it has interesting physics. And the interesting physics, the thing that attracted attention in the mid-90s on this material, is that it is actually a superconductor with unconventional pairing at very low temperature, in contrast to cuprates. Below 1.4 Kelvin, you can't see this in that plot, the resistivity drops to 0, and that was discovered by Yoshima Eno and co-workers, I think, in 1994. And ever since, theorists and experimentalists have been debating what the nature of this superconducting ground state is. But it also has very interesting transport properties at higher temperature. Between 1.4 Kelvin and 25 Kelvin or so, it's a Fermi liquid with a T-square resistivity. And then as you heat up to higher temperature, the resistivity grows and never saturates and becomes very large. So it sort of beautifully illustrates this necessity of describing the evolution of the system as a function of energy scale. Here at high temperature, very high temperature, you see 1000 Kelvin, we have very incoherent transport with very short mean free path. As we flow down, we go through different regimes of resistivity. Eventually, we reach Fermi liquid, and at lower temperature, even we go to a superconductor. So there is this whole history of behavior as a function of energy scale, and we would like to describe that. Okay, so what is the electronic structure of this material? It has a beautifully simple electronic structure. If I focus only on the active states near Fermi level, you can think of it in the following way. Everything you have to discuss is basically taking place in the ruthenium oxide planes that I just mentioned. You have the ruthenium orbitals, which are these d orbitals here with 4 lobes. And in between, you have the oxygens with their p orbitals. And these orbitals hybridized by pi bonding, to use the terms of chemistry. If you take the dxy orbital in the plane, it hybridizes very naturally with pi bonding with the p orbitals like this. So it should give a very two-dimensional band in this square plane. Right? And this two-dimensional band, which is derived from the hybridization of dxy with pxpy, is the so-called gamma sheet in the Fermi surface, which is this sheet here. And you see that apart from these little ears here, this gamma sheet is relatively circular, right? So it's a nice two-dimensional sheet. Now, if you focus on the other 3 orbitals of the so-called T2G manifold of the d orbitals, the xz and yz, so these are directional, here, in the z direction. So you see these orbitals, say the yz, hybridize along the y-axis, and along the z-axis, but the other plane is very far away, so that z-axis hopping is very small. But it has almost no hybridization along the x-axis. So this should give rise to basically a very one-dimensional band along the y-axis. And a one-dimensional band should have a Fermi surface which is just 2 vertical sheets. So it should be something like this, here and here. Okay. Similarly, the other guy here, the xz, is the opposite. It's along the horizontal direction. So it should have a Fermi surface which is this and this. Of course, life is a little bit more complicated than that. There is actually hybridization between these orbitals. And so these 2 vertical and horizontal things have actually hybridization near the zone diagonal, and so they reconstruct into this squarish beta sheet, and these other squarish things centered around pi here. So you see, you should think of this and this as resulting from horizontal and vertical Fermi surfaces, which are reconstructed along the diagonal. Okay, so you see how you can make sense of a rather complex 3-sheet Fermi surface from very simple consideration of chemical bonding. Incidentally, this is also why DMFT is nice, because it allows you to talk to chemists much more easily, because you talk the language of atomic orbitals and atoms. If you come and see a chemist and show a chemist a bunch of cone-sham bands, you know, all these spaghettis, half of the time the chemist will turn away from you and say goodbye, okay? But if you actually start talking about hybridization, bonding, anti-bonding of atomic orbitals, right, then there's a chance the discussion can continue. So this is an important aspect of the theory, is that you have this duality between thinking about in wave-like cone-sham language or thinking in the atomic orbital language. Okay, so this is the electronic structure of strontium ruthenate, at least the low-energy electronic structure. I'm only describing the low-energy bands. So this is actually a band structure calculation. There is, of course, a bunch of bands, but here I've displayed those around Fermi level, which is here. spanning about 4 eV around Fermi level. And you see these 3 bands here in red are derived from these 3 bonding mechanisms and correspond to these 3 Fermi surface sheets. Now, you can ask here, at any given point on the Fermi surface, you can ask about the orbital composition of my block states, right? So precisely this means the value of this matrix element, psi k nu chi m, at the given k point and for that given band. So you can ask, you know, at this point, for example, what is the dominant orbital composition of that beta sheet or that gamma sheet? And this is displayed here. So here, what has been done is to calculate psi k nu chi m modulus square, so the orbital composition at a given k point for a given band, to plot it for the xy projection and the xz projection. And the color intensity denotes whether the percentage is 0 or 100. And so what you see here is that if I look at the gamma sheet, the gamma sheet is almost completely xy, 80%, let's say, xy here along the vertical direction, very little xz, while the beta sheet is almost completely xz-yz, and very little xy, in complete agreement with that bonding picture I mentioned before. But if you look here on the diagonal direction, you see that it's much more mixed. The gamma and the beta sheet have about 50% xz-yz and also 50% xy. So why is that? The reason of that is spin-orbit coupling. The description I was mentioning here ignores spin-orbit coupling. If you turn on spin-orbit coupling hybridizes these different orbitals, right? And so it's active along the diagonal direction, and it's also responsible for this little ear here. If you turn this into the band language, this is a calculation with no spin-orbit coupling. You see these band crossings, for example, here. And spin-orbit coupling acts as a level of repulsion. And so this band crossing is lifted by spin-orbit coupling. You see this here, you see this there, and so on. Okay. So this means this psi k nu chi m matrix element is strongly angular dependent. It's going to be, I mean, this basically is the angular dependence of these matrix elements. So keep this in mind. Okay. So how are we going to do DMFT on this material? So one way to do it, which is sort of the sort of cheaper way, massively downfolded way to do that, is to construct Vanier functions just for those bands. So we take a window, which is this 4 eV window, and we construct Vanier functions from just these 3 bands. Of course, those Vanier functions are going to be quite delocalized, right? Because they capture the hybridization with oxygen. An alternative way would be to take a much bigger window and to construct our Vanier functions from this big window. In that case, our Vanier functions would be very localized. They would really look like atomic orbitals. You would have to use different interaction parameters, much larger, for this description, but you can do that too. Here, the calculations I'm going to present are done in this massively downfolded picture in which you just retain 3, you construct these quite delocalized Vanier functions for these three bands. So the next question is which interaction parameters do we have to add to this correlated subspace? And again, this is a question which is outside the framework of DMFT. DMFT does not provide an answer to that question. You have to get this interaction parameter externally. So either you do it by your inspired guess or comparison to experiments, Or you do it by some other ab initio scheme that will allow you to give some prediction with some confidence level to the value of these interaction parameters. Or you move beyond just DFT plus DMFT, and you aim at a fully first principle approach to electronic structure based on DMFT, and that will be the topic of tomorrow's lectures, how to do this with combining GW and DMFT. For the moment, I'm going to assume that these parameters are just given to us. Yes, please. Yes, Fermi surface. Okay, so let me try. I'm not sure I completely understand the question. The question was how we identify the different pockets, I think, of the Fermi surface, right? So in practice, what you do, of course, you do a DFT calculation of the band structure, right? And you can map where these different bands cross the Fermi level. Fermi level is here. You see, this is moving from X to gamma. So gamma is here, X is here, right? I should find 3 crossing points, 1, 2, 3, right? And here you see indeed 1, 2, 3, right? On the other hand here, if I move from gamma to M, I should see only 2 crossing points corresponding to the beta and the gamma sheet. And indeed, when I move to gamma to M here, I see 2 crossing points, 1, 2. Of course, this plot here follows a very specific path in the Fermi surface. It does gamma, M, X, gamma, and then Z, which is the next layer on top of gamma, right? But I could repeat that exercise for any K point in the Brillouin zone, and hence map the Fermi surface from the band structure. And if I do that, I find 2 sheets, which are the beta and gamma sheet, which are centered on gamma, and 1 sheet which is centered on pi pi, which is X, which is the alpha sheet. Did that answer your question? Yes. Okay. Okay, so I was with interaction parameters. So if we had a single band, the only interaction parameter which is local we can consider is U and up and down. But now we have a multi-orbital system, and so we have more freedom, right? We have, in this specific case, 3 orbitals to consider. And fortunately, people have done a long time ago a sort of group theory classification of the sort of interactions that can emerge. And assuming some symmetries, I don't want to enter too much into the details, but assuming some symmetries, what comes out of this analysis, and you can find details in this famous book, for example, Multiplets of Transition Metal Ions and Crystals. The effective interaction for this 3 orbital system is called the Kanamori Hamiltonian. And the Kanamori Hamiltonian contains basically 2 interaction parameters. One is U, which is our famous Hubbard U, which is the cost for putting 2 electrons with opposite spins in the same orbital. So you see NM up, NM down, same orbital, opposite spins, cost U. Now you can also put 2 electrons in different orbitals, but with opposite spins. Opposite spins, but different orbitals, that cost a little less, because obviously the orbital overlap is a little less. And that's called U prime. And for perfectly cubic T2G, blah, 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 it can be shown that this U prime is actually related to U by U prime equal U minus 2J, where J is the intraatomic exchange, also called Hund's coupling, for the reason you will see in a minute. Now, the next thing we can do is we can put 2 electrons in different orbitals with parallel spin. And those of you who know a little bit of chemistry probably know that this is the most favorable configuration. That's called Hund's rule, right? And when it comes to modelizing this by an interaction Hamiltonian, this means that this should come with the smallest energetical cost, because this is the most favorable configuration. And indeed, the interaction is U prime minus J. So again, the interatomic Hund's coupling, the same J, lowers that energy cost from U prime to U prime minus J. And because U prime is U minus 2J, this interaction is actually U minus 3J. Okay, so these are all density terms, 3 terms. And then, because of overall symmetries, there has to be additional terms that cannot be expressed at density. One of these is called the pair hopping terms. You see, this is like a pair of electrons in orbital m with up and down that are coupled to the corresponding pair of electrons in orbital m prime. So this is like hopping a pair between 2 different orbitals. It also comes with a coefficient J. And there is another term, which is more like a spin exchange term, which comes with the coefficient J as well, and a different sign. So this Hamiltonian is the 3-orbital Kanamori Hamiltonian. I cheated a little bit, because for a tetragonal system, which is not cubic, the xy and xz are different, right? So the u in the xy orbital has no reason to be the same than the u for xz. And so this Hamiltonian is a little bit too symmetric, okay? But let's keep this in mind as a cartoon for this system. If you want to be more sophisticated, you can use a slightly more complicated interaction Hamiltonian. This is a good first approximation. In fact, for those who are interested, the u, xy, xy, and xz are only different by about 15–20% in this material, from what we know from, say, constrained RPA or whatever. Okay, so this is our interaction Hamiltonian, and so now what we are instructed to do is to actually solve this self-consistent DMFT impurity model with that interaction Hamiltonian, but we have to pick values for u and j, right? And again, these values are not dictated by DMFT, they are dictated by the electronic structure of the system and the downfolding procedure. And you can either compare 2 experiments and pick the u and j that do the better job, or you can do things like constrained RPA that I will describe tomorrow, or now more sophisticated GW+EDMFT. Turns out that for this material, the value of u and j are not very much up for negotiation, because there are tens of papers that have actually demonstrated that the proper value of u and j to describe the physics of this material are basically in this range. So u is about 2.4 eV, and j is about 0.4 eV, give or take 10%. And please note that this value is actually not very large. You saw that the bandwidth of this manifold was 4 eV. So this u is only about, let's say, half of the bandwidth, or 60% of the bandwidth. Okay, very good. So what happens when you do that? You apply DMFT to this material, and this was done in this paper by Jerne Mravlje, who is has been now back in Slovenia for many years. It's already a pretty old paper. And what Jerne discovered when doing this work is that if you actually, so, you know, we varied J here just to investigate the physics of this system. U was fixed to, I think, 2.3 eV in this case, and J was varied. And these tables give you, as a function of J, for few values of J, the effective mass of the quasi-particles for the xy and xz, yz orbitals. Xz and yz are equivalent. Normalized to their DFT values in the LDR approximation. And so you see, if you put no Hund's coupling, if you just have the U, right, then you find that the enhancement for the XY band is only about 1.7. And this is in blatant contradiction to experiments. Experiments, again, the value of the effective mass are known extremely precisely from quantum oscillation experiments, for those who know what this is. Those who don't, we can talk at the break. And it is known that the effective mass enhancement for the XY, or the gamma band, basically, is of order 4 to 5. The precise number is known. And for XZ, YZ is about 3. So it is a very strongly correlated material. And it cannot be explained just by you. Not you and me, but you, about you. It can be explained by you and me with DMFT. Now, what Yanni discovered is that if you crank up J, then all of a sudden everything works fine. So the effective mass enhancement for the XY becomes of order 4.5, and for the other one about 3.3, which is very close to the experimental values. And also, you see that something interesting happens, which is that with only U, the two enhancements were the same, and now they become differentiated. The XY has a larger mass enhancement than the XZ-YZ. So now this is a little strange, because actually if you look at the band structure, the XY band, the XY dominant band, which gives the gamma sheet, is this very broad band here. It has a width of about 4 eV. And the XZ-YZ only have a width which is about half of that. And nonetheless, it is the broadest band that gets the largest mass enhancement. So that's a little weird. You know, if you are familiar with mod physics, you would think the opposite, right? The broader band should get the lower mass enhancement. So what's going on? Well, I mean, if you look carefully at this band structure, you will see that the XY band has a Van Hove singularity here. Van Hove singularity is a big word to just say that the dispersion becomes very flat here around the endpoint. So there is Van Hove singularity very close to Fermi level, which leads to a peak in the density of states, very close to Fermi level. And flat band means very low kinetic energy, right? Because the band has low dispersion. And that's why actually correlation effects become very strong for the XY band, right? Because what counts is not the overall bandwidth, but actually the available kinetic energy close to Fermi level. But interestingly, this physics is only revealed in the presence of the Hund's coupling. So the Hund's coupling plays a role of orbital decoupling. It allows the different orbitals to have more independent life, and now the XY becomes sensitive to Van Hove. So in a nutshell, this material is correlated because of the Hund's coupling, not because of U. And on top of that, the Van Hove singularity also plays an important role. So it's a Hund-Van Hove metal. Okay. Good, so let me elaborate a little bit on this. Sounds very promising. So can we actually really test the ability of DMFT to describe this material beyond just a few numbers in a table? Can we actually test that? And this was mentioned by Hugo in his lecture this morning, but I want to elaborate a little bit on this. This was done much later in a relatively recent paper by my photoemission buddies, Felix Bamberger and Anna Tamay, and co-workers in Geneva. And these people have really an exquisite RPS photoemission apparatus with laser source, which allows to reach remarkable resolution. This is probably the best RPS Fermi surface you will ever see. Well, not ever, perhaps in the future, but you've ever seen. Very, very high resolution. And one can also map out the full dispersion of quasi-particles. So what was done in this photoemission experiment is one takes angular cuts, like this. So these are different angles in the Fermi surface, from horizontal to diagonal, different cuts, from 0 degree to 45 degree. And one follows the dispersion of the quasi-particles as a function of energy and momentum along these different cuts. So here is the beta sheet, which disperses. You see a little bit of the gamma sheet here, it's fainter. And as you move to 45 degree here, you should see 3 quasi-particle sheets, and indeed beta, gamma, alpha. You see that close to Fermi level, which is at 0, these quasi-particle dispersions are very sharp, which should be, because this is a good metal with sharp quasi-particles at low energy. As you move away from Fermi level, the lifetime becomes shorter, the width becomes larger, and you see that there is traces more fuzzy. But this is a very beautiful determination of the quasi-particle dispersions in this system. So now that we have these quasi-particle dispersions, one can actually reconstruct, one can try to extract the self-energy directly from experiments. Before we do that, we can first focus on the Fermi surface. The Fermi surface, I explained briefly before that this little ear here is due to the spin-orbit coupling. Indeed, if you do a non-spin-orbit coupling calculation, you will find that there are these weird crossing, which are the dashed line between these Fermi surface sheets. But once you turn on the spin-orbit coupling, because of level repulsion, these crossings disappear. And so this distance here in k-space between the different sheets should be a direct measurement of the effective strength of the spin-orbit coupling. And if you do a DFT calculation, you find that this splitting, which is this lambda spin-orbit coupling from DFT, is about 100 millieV. And it turns out that this is a factor of too small to explain, to reconcile with the measured Fermi surface. And in fact, it was a prediction from theory, first from perturbation theory, then from DMFT. I think I have the reference somewhere, I don't know where. Yes, here. These are the references that first predicted that correlation effect should enhance this effective splitting by about factor of 2. So it's not a small thing, from 100 MeV to 200 MeV. And indeed, this was the first conclusion of this experiment, that indeed this enhancement is there. So first good prediction of theory. Then we can go one step further and actually extract the self-energy. So how do we do that? So the most naive way of doing this would be to just take the trace of this quasi-particle dispersion, start from the point where it intersects the Fermi level, which is here, right? And then we take this K point, we measure this energy difference, and this should be precisely equal to the value of the self-energy at this K point, and hence at this energy. Right? So there is a little catch here, which is that I neglected, in this analysis, I neglected the off-diagonal elements of the self-energy in band space. So sigma nu prime with nu different from nu prime is neglected in this analysis. One can check that it's actually very small. Okay, so when one does that, one repeats that just from these experimental traces, there is no theory there, for the different angular sectors. And when you do that, this is what you find. So this is the real part of the sigma nu self-energy for the gamma band in green and the beta band in yellow, for binding energy up to 60 MeV for the different angles, right? So this 0 degree, 45 degree. And so you see that this self-energy has considerable angular dependence. So if you are too naive, this sounds very bad for DMFT, right? It means there is very strong momentum dependence, at least along the Fermi surface. So what's going on? Well, you just have to remember that DMFT is not saying there is no angular dependence. It's saying that when you go to the local orbital basis, it should be momentum independent. And what we just measured is this, not this. So we can actually go back to the quasi-particle equation in this form. Instead of writing it in band space, we are going to write it in orbital space. So now it becomes a matrix equation, determinant of something equals 0. You see that this is a nonlinear equation for omega. And we can take the data and extract, by solving this nonlinear equation, extract omega of k. And measure omega of k and extract sigma. Okay, so this is what was done. And when you do that, this is what you find. So this is, and again, the only input here is the photoemission data. And what you find when you do that is that in orbital space, this angular dependence becomes minimal, and this mess here can be rationalized by saying that there are two self-energies, one for the xz, and one for the xy. Of course, there is some scatter, so maybe there is some little residual angular dependence, which would be beyond single-side DMFT. I'm not saying single-side DMFT is totally perfect, okay, for this material, but at least it's close to being a very good, it's a very good approximation. Right? So this is the self-energy of the xy orbital, and this is the self-energy of the xz orbital measured up to 60 MeV. It would be wonderful to have such a precise set of data for larger binding energies, but you can't really do that with laser RPS, at least not with this laser photon intensity. And again, you can compare this to DMFT computations with this value of U and J. And these are the plane lines, and you see there is excellent agreement with the data. Now you can do more than that. You can actually compute the whole dispersion of quasi-particles. And what you see here for each of the angles is actually a color map of the DMFT spectral function, superimposed with the white dots, which are the RPS derived, the RPS measured quasi-particle dispersion. And you see that there is fairly good agreement all over the angular sectors. So this is kind of a direct test of the ability of DMFT and its local approximation to actually describe at least the quasi-particle physics of this material. Any question about that? Okay, so what have we discovered? So we've discovered that the locality assumption is pretty good for this material, even though it's a 2D layered material, multi-orbital. It's actually a good description, and it's a little puzzling. Why is that so? As you know, DMFT formally can be exactly derived from the limit of infinite dimensions. Why does it apply so well to 2D? So that's a question, which I'm going to try to answer in the next slide. We've learned that the Hund coupling can be the main source of strong correlations, and other features of electronic structure like von Hove are important. Okay, so Hugo already sort of provided a spoiler to the answer to the first question. Why is DMFT not an absurd approximation to do for this material? Well, the answer to this question is that dimensionality is not really the point. The point is how long range or short range are the important correlations in this system. In other words, DMFT is going to work well when the correlation length for any sort of emergent order or quasi-order is small enough, because that's when the locality assumption is good. And we know from neutron experiments on this system. And we know that at low temperature, say just above the superconducting transition, 1.6 Kelvin, of course, correlation length grows as you cool down. So this is kind of an up or down. The correlation length is only about 2.5 lattice spacing. So even though, as you saw in Hugo's lecture, the measured susceptibility in this system has these spin density wave peaks, the width of these peaks, which gives you an estimate of the correlation length, is only about 2.5 unit cells. Right? And so there are not really very long-range spin fluctuations in this system. They are, I would say, medium or short range. And very likely this is why the DMFT approximation is actually good. It also means, by the way, that even though it's only 2.5 unit cells, it's not 0. It's not 1, right? And so there should be some contributions from longer range spin fluctuations to the self-energy, which are not included in single-side DMFT. Perhaps this is responsible for that slight angular dependence, More importantly, it could be responsible for momentum dependence across the Fermi surface, which I haven't tested from these experiments. And in fact, it's a good system to explore generalization of DMFT, including longer-range spin fluctuations. So it's in the hands of your generation of doing this sort of thing, going beyond single-side DMFT, including spin fluctuations, beyond the locality assumption. Okay, so that's kind of a rationalization, and Hugo has already shown that now from DMFT we can actually calculate the full two-particle response and obtain good agreement with the neutron scattering experiment. So I'm not going to elaborate more on this because Hugo already mentioned this. I just want to make one point, which I don't remember if Hugo made in his talk, which is that we can also test the relevance of the Hund physics from this. And in his paper on this topic, what Hugo did is that he monitored the continuum background. You see this yellow background here, which is also seen in experiments, as a function of J. And he could show that this background is actually due to the Hund coupling. So it's kind of a direct probe at the two-particle response level that indeed Hund physics is important to explain the observed neutron signal. Okay, so this sort of closes to some extent what I wanted to say on strontium ruthenate. And now, let me first ask you, do you have questions on this? Yes? So now you are talking about the long-range nature of the interaction, right? Okay. So that's a very good question. In all these calculations, the long-range interaction was just not taken into account for the correlated embedded problem. It's implicitly taken into account in the DFT computation, of course, which treats the electrostatic interactions at the Hartree exchange correlation approximate level. If you were to include the long-range interaction in the single-side DMFT framework, you would be bound to just do the Hartree approximation for those, because that's what single-side DMFT does. It tells you if you have long-range interaction in your correlated shell, it has to be treated at the Hartree level. So the longer-range interactions are not treated dynamically in single-side DMFT. They are just treated at the level of Hartree approximation. So the only thing they can do is to actually shift the different bands with respect to one another. Now, if you want to do more than that, and sometimes it's important, you need to go beyond the DFT plus DMFT formalism. You have to do GW+DMFT, for example. So that I will talk about tomorrow. Sorry? Yeah, so then, right. So in that case, you would have a fully, spatially dependent screen interaction, which will be treated at the GW level. And I will come tomorrow. More questions? Can you speak louder?
As you mentioned, there is a one-hot singularity.
Yes.
But why there is no such strong ferromagnetic operation? And
Why is there
is no ferromagnetic operation caused by strong criteria?
Yeah. So that's a very good question. So actually, there are magnetic correlations. You saw these peaks, right? These peaks are actually associated with the nesting between the flat regions of the Fermi surface. So in fact, this material has some spin density wave correlations. However, in the pristine materials, they are not long range. But if you substitute, for example, on the ruthenium side or on some of the other side, you can actually induce a magnetic phase in this material. So it's not so far from a magnetic instability. So that's also true. Okay, so I'm terribly late, so I will have to cut some of the things. But the thing I want to do next is actually to put this in a slightly broader context. So we've discovered that strontium ruthenate Hund coupling is essential to the physics of this material. And I want to put this in a broader context. It's not only the case for strontium ruthenate, but it's actually the case for a very broad range of material, which we call Hund metals. And for those interested in sort of a high-level, non-technical description of this, my friend Gabi Kotler and myself, we published a paper in Physics Today giving such an overview of what we call Hund metals. But this has been a long story that has lasted for now about a decade and a half. The concept of Hund metals really emerged when the iron superconductors were discovered in 2008. That's really what triggered the awareness that Hund coupling is important to understand strong correlations. So I want briefly to put this in context. So yeah, that's the high-level summary. Not only you, but also Jay. Okay, good. So let me skip some of that because, yes. Okay, so you probably know that there are two time-honored routes to strong correlations. There is mode physics, discussed a lot in this school, and also heavy fermion physics. Heavy fermion is when you have two different entities, heavy and light electrons, and they hybridize from a Kondo system and leads to very large effective mass. So what we've discovered is that there is actually another route, which is Hund physics. So there are really these three routes to strong correlations. And as I just mentioned, it's not only strontium ruthenate, but it's many materials. All the iron-based superconductors are actually Hund metals. And also, most of the transition metal oxides of the 4D series, not only ruthenium, other of the 4D series are actually Hund metals. And the reason of this is that for those 4D materials, the U is not so large, so they are not close to Mott insulators, except for half-field shell. And J is really important. Okay, so what is what distinguishes Hund metals from, say, metals which are close to Mott transition? In metals which are close to Mott transition, you have local moments and narrow bands. In Hund metals, the bands are wide, right? The systems are very good metals at low temperature. Strontium ruthenate is an excellent metal, but nevertheless, they display very strong correlations. So there is no sign that they are close to a Mott transition, but still they have very strong correlations. So let me explain briefly why. And then I will take, I don't know, 5, 7 more minutes. Can I do that? Just to wrap up things and tell you everything I didn't want to tell you. I didn't have time to tell you in just a nutshell. Okay, so I'm going to try to be brief. Okay, so the first thing I want to explain is why having a Hund coupling can take you away from Mott physics. And that's actually very simple to understand. A rough estimate of the Mott gap in a system can be done by computing the energy difference between adding an electron and removing an electron in a shell. So what you do is you do E of n plus 1 plus E of n minus 1 minus 2 E of n, and you compute that quantity, and this gives you an idea of the effective interaction in the shell. So if you actually do this, I think I have a better cartoon that will explain that. Yes, maybe that's better. So if you do this for a half-filled shell, like here we have these 3 orbitals and 3 electrons, so it's exactly half-filled, right? When you add an electron, you have to create a double occupancy. no other way. Right? And so you will have to pay the full price of U. But if you don't have a half-filled shell, like here, you never have to create a double occupancy. So you will never see the scale U. You will only see the scale U minus 3J. So this little calculation will tell you that for a half-filled shell, the effective U is U plus, in that case, 2J. But for a non-half-filled shell, the effective U is U minus 3J. And the mod criterion is basically this effective interaction of order the bandwidth. So you see that for non-half-filled shell, the critical U will be the bandwidth plus 3J, so it's going to be very large. While for a half-filled shell, the critical U will be the bandwidth minus 2J, so it will be reduced. Right? So this is why half-filled shell have a big tendency to be mod insulators, in contrast to non-half-filled shell, which can be much more metallic. And that's true for all oxides. You can check that. Okay, so from this argument, you can understand why, when you turn on the Hund's coupling, so this is a plot of Z versus U for different J. And you see when we increase J, what happens is that the mod transition, this is a non-half-filled shell, 2 electrons in 3 orbitals, the critical U is pushed to large value. Okay, so from that perspective, it would seem that as you turn on J, you get further and further away from mod physics, and the system should be less and less correlated. But nature is more perverse than that. In fact, what you see is that in the metallic regime here, what happens is that as you increase J, yes, indeed, you push critical value of U to larger values, but actually Z goes down. So you correlate the system more. The effective mass becomes larger. So why is that? Again, I have a cartoon that explains that. Think of this hopping process of electrons between these different valence configurations. Now J is important, so this restricts phase space. The hopping has to be between maximal spin configurations. So when you hop that guy here, there is no way you can hop to a configuration that would have, a lower spin. It has to be maximal spin. So that constrains the phase space for hopping a lot. Hence, it slows down electrons. That's said with hand-waving words, but it's really true. When you do the mathematics, you can show that this pushes the coherent scale of the electrons down to low energy. So there's this dual aspect of the Hund coupling. It pushes the critical U to large values, but it also reduces Z. Okay, good. I'm going to skip a lot of things here. So actually, this is kind of a map that we draw in some review article a long time ago, which shows as a function of number of electrons in the shell for a T2G shell from 0 to 6. The black bars denote where the mod insulators are. And as you increase J, they move in this direction, while for the half-filled shell in that direction. And we try to locate a bunch of materials in this phase diagram, and you see that here the color plot is such that lighter color means more correlation, smaller Z. And you see that many of the transition metals of the 4D row, except for the half-filled shell, are strongly correlated, but very far from the mod state. That's the message of this plot. Okay, so now let me finish this business about Hund metals by mentioning, going back to this notion of quenching the fluctuations of that atomic multiplet as we go from high energy to low energy, remember, from the beginning of the lecture. So we discussed the fact that in this case, which is relevant for strontium ruthenate, the ground state of that guy is 9-fold degenerate. So as we flow down to low energy, this 9-fold degeneracy has to be gradually lifted. And how does that happen? Well, it happens that for this multi-orbital impurity model, the scale at which the orbital fluctuations get quenched is distinct from the scale at which the spin fluctuations get quenched. So the threefold degeneracy due to orbital fluctuations gets quenched at a scale which is the orbital Kondo scale in technical terms, which is very large. We estimate it to be like several hundred or perhaps 1,000 Kelvin, while the scale for the eventual quenching of all fluctuations is very low, and it's this Fermi liquid scale of 25 Kelvin. So this means that there are really three regimes. There is a Fermi liquid regime here below the spin quenching scale. There is an interesting intermediate scale where spins are fluctuating, but the orbitals are not fluctuating. And there is a very high energy regime, perhaps not really reachable in the experiments because the system will have melted, in which everybody is fluctuating. And I don't have time to discuss that in any details, but there are some experiments that directly test that or indirectly test that. One experiment that tests this is the so-called Seebeck coefficient, which is the thermoelectric power of the system, which is to some extent a measurement of which degrees of freedom fluctuate in the system. And it can be shown that the value of the Seebeck coefficient in this intermediate temperature regime is actually in agreement with the notion that spin fluctuates, but not orbitals. And much more recently, there was a measurement of Rick's spectroscopy for this material that were able to track down both the spin and the orbital fluctuations and compare to DMFT, because now we can calculate two particle properties. And it was shown that indeed the orbital fluctuation scale is higher than the spin fluctuation scale, and actually DMFT does a pretty good job reproducing the Rick spectrum. Okay, so I'm not going to tell you much more about Hund coupling, because obviously I'm already way past my time. I just want to do a little bit of advertisement. There is a nice paper that we published recently on this very heavy mass oxide, lithium V2O4, which actually demonstrates that Hund coupling is actually very important in this system to explain the large mass. And this was also a very interesting system because it has a very, very low Fermi liquid scale, which is a couple of Kelvin. And so it was kind of a challenge to impurity solvers for DMFT. Okay. Another topic I'm not going to have time to discuss, obviously, but I'm going to do a little bit of advertising, is that one can actually compute very delicate low energy properties with DMFT and with appropriate computational technology, namely things like transport. I'm going to skip these things that I'm not going to have time to discuss. But transport in DMFT can be computed in the Kubo formalism, and it's not, in fact, a two-particle calculation, because in DMFT, because the self-energy is local and the matrix element of the current are odd, it turns out that the current correlation function doesn't have vertex correction, so you can get everything from the bubble. So from this formula here, in contrast to spin and charge, which require the whole machinery of vertex corrections that Hugo described. And a bit of shameless advertising with many people who are in the room, Harry, Jenny, David, and so on. We published recently a bunch of papers in which we attempted, successfully, I think, to compute transport in strongly correlated oxides and less strongly correlated oxide down to very low temperature, down to the identifying the t-square coefficient of the Fermi liquid regime. And this actually requires a very precise determination of the scattering rate at low frequency. So it's a completely different game than computing this photoemission spectrum. It's actually a much more delicate game in which what you really want to know is the value of this function, which is the imaginary part of the self-energy, at very, very low frequency here. You see, this is the imaginary part of sigma of omega in real frequency, computed. Obviously, I'm not going to enter into any of the details. We can discuss during the breaks. Computed from a combination, actually comparing numerical normalization group solvers to continuous time hybridization Monte Carlo solvers plus some analytic continuations. And you see the Fermi liquid regime should be omega square. So omega square is really, where is the pointer? Oops, great. Obviously, my computer doesn't want me to finish these lectures. Yes, okay, so you see that omega square is only living here, right? And that's what you need to resolve. But there is a lot of structure beyond the Fermi liquid regime in these self-energies. But what you really want to resolve to get transport is the value of this thing here at very, very low frequency. So people interested in the details of the methodology to do that can look at some of these recent papers, especially the first three ones. Okay, so now it's time for me to actually conclude. I wanted to tell you a bit about beyond single-side DMFT. Maybe I'll try to integrate a little bit of that in my lecture tomorrow. Obviously, I don't have time to do that now. I just want to jump to conclusions, and then we'll all go to lunch. So actually, let me jump to conclusions. Yes, here. Okay, so what is the take-home message, perhaps, of all the school, is that dynamical mean field theory and perhaps more broadly generalization of embedding techniques combined with electronic structure is really a very powerful tool to not only calculate but also predict and understand the physics of strongly correlated electron materials. There are many opportunities for further developments. DMFT is now a very mature field, so I've tried to outline on this poor depiction of a tree the sort of developments of DMFT. So there is this conceptual core, which is basically what we describe in these lectures, embedding this and that. There are many, many applications to both models and materials. And there are also many extensions going beyond single-side DMFT. So, you know, GW+EDMFT, cluster extension, extended DMFT, and so on. And all this is rooted in very important technical developments about basically impurity solvers and also combinations with electronic structure. So the roots of this tree are really what feeds the whole thing. It's really the technical developments that are really crucial to the development of the field. By now, there are review articles basically on all the branches and roots of this tree. So you will see this in the slide. I've tried to put relevant review articles. This is probably already a little bit outdated, but there is a bunch of review articles on many, many of these different aspects. And given the topic of the school, it would be unfair not to mention that to the whole enterprise, having an efficient and sustainable open source software environment, not only Trix is of course the best. Actually, now it's time to remove my sweater. Here we go. You see? Trix is great, but it's also nice to have other people developing similar things. And so I've tried to outline on this slide, perhaps it's incomplete, many other software enterprises throughout the world that implement quantum embedding and DMFT methods computationally. And it's a very lively ecosystem of codes. What else do I want to say? I don't want to leave you under the impression that DMFT is only being applied to transition metal oxides, and especially old-fashioned ones. There are many materials of very recent interest to which DMFT is applied. For example, the infinite layer nickelates and other nickelates. Harry is an expert, for example, but also moiré materials like TBLG and two-dimensional dichalcogenides are a very good testing ground and very good opportunity to use DMFT. There are many papers on that. There are also papers on fancy superconductors like uranium, tellurium-2, and things that are, topics of current interest in our field. But there is work ahead, right? And work ahead is, for example, developing ever more efficient impurity solvers. We would like to do more orbitals. We would like to have a better resolution at low energy in real frequency. Maybe tensor networks are the way to go there. We would like to have better impurity solvers to handle retarded interactions, and that's going to be important in the GW+EDMFT context tomorrow. So that's definitely something we need. We want to advance towards a fully ab initio electronic structure framework with DMFT, and that requires to go beyond DFT. That will be the topics of the lecture tomorrow, GW+DMFT and perhaps beyond, and so on and so forth. I think that's more or less everything I wanted to say. I want to do a little bit more advertising for people who want to be continuously exposed to the latest development in the field and also applications to material. You can follow an online symposium that we created a couple of years ago at CCQ. It's every month, 2 talks every month. You can see the announcements on the CCQ website, but you can also subscribe to the mailing list and receive the announcement in your inbox. It will resume sometime in September this year. There are some lectures, more detailed lectures you may want to see on my Collège de France website. And what else do I want to tell you? Shakespeare anticipated DMFT in this beautiful verse from Hamlet, which I think exactly describe what DMFT is about. We are bounded in a nutshell. This is the atom. But we are the king of infinite space because we can describe the solid. Right? Shakespeare was really a genius. And I will leave you with this quote from P.W. Anderson. Okay, that's it. Sorry for being so long.